Okay, so we've done our simple example of one particle moving in one dimension, and we figured out that it's the pressure that it exerts was mv squared over capital V. That's the volume of the box. So now let's allow it to move in more than one dimension. So let's assume, like it's shown in this picture here, that it's moving at some angle. So it has an x component of its velocity and a y component of its velocity. And there could be a z component, I just didn't draw it here. So we have to go back and think about what has to change in what we did before. One thing we have to think about is, how about the time between collisions with the left wall? What is it now? Is it the same as before? There's a couple other choices, A, B, C, or D. Does it 2L over Vx, 2L over Vy, or does it depend on the collisions with the top and the bottom? So take a moment and pause the video, see if you can commit to one of these answers before we go on. Okay, did you select your answer? Hopefully it's not too hard to realize that how far it travels in the x direction, and this direction is x here, depends on the speed in the x direction, or the x component of the velocity. So if the velocity in the x direction changes, it will change the time between collisions with the left wall. So it's going to be 2L over Vx. I need to focus, if I want to know the collisions between the left and the right wall, the time between those collisions, that depends on the x velocity. So 2L over Vx. You might worry about, does it matter about the collisions with the top and the bottom? The answer is no. So you can imagine it comes in here with some Vi, and then it bounces off the top, and then comes out with some Vf. But remember, momentum is conserved in this collision, and there's no force in the x direction. So there's no force in the x direction. So when it hits the top or the bottom, no force in the x direction, the x velocity doesn't change. The only time the x velocity changes is when it hits the left and the right wall. So Vx doesn't change in these collisions here. Unchanged. So the answer to this one is 2L over Vx. The collisions with the top and the bottom don't matter because they don't change any speed in the x direction. And so what I get, to make it in a one particle in 3D, my pressure is going to be mvx squared over v. Nothing else changes in the analysis. So F equals delta P delta T, that's still the same. The only thing that's different is the time between collisions, which now depends on the x component of the velocity. Okay, so that's the first modification. Now we need to think about, what if I have multiple particles going around and doing this? How do we generalize it in that case? Okay, so we've thought about now, if I have one particle in the box moving, even if it's moving in all three directions, the pressure that it exerts on the left wall is given by this formula. PV is mvx squared. So again, capital V is the volume. This is the mass of the particle. So small m is mass of the particle, and Vx is the x component of velocity. What if I've got two particles? Well, I just need to think about the pressure caused by each one. So I would have something like this. P1, that's the pressure for particle 1, times V would be equal to mv1x squared. And I'm going to assume the masses are the same for all of them. It's just to make my life easier. And then the pressure from the second particle would be similar, mv2x squared. And the pressure from the third particle would be mv3x squared. So the pressure from each one depends on the mass of each one times its x velocity squared. What if I want to know the total pressure? Just add them all up, right? So add everything up. I would have P total times V, and I'm just going to call it P, just because that'll be the total pressure. So P times V will be equal to M times v1x squared plus v2x squared plus v3x squared. However many particles I have, add them all up. Okay. So this is now many particles moving in many directions. I have this formula. You might be worried about, well, what if the particles collide with each other? Doesn't that make things more complicated? And the answer is no. So collisions don't affect this. And the reason is because the collisions conserve momentum. And the amount of force that is exerted on the wall is related to the amount of momentum change that the wall is causing, right? And so even if the particles are all colliding with each other, the total x momentum is not changed. So the total momentum in the x direction is never changed by any collisions. So I have the same amount of x momentum being changed by the wall, regardless of the collisions of the particles. So the collisions don't affect this because momentum is conserved. In collisions. And so the total change in x momentum caused by, let's say, the left wall is independent of the number of collisions. It's also independent of the collisions with the top and the bottom and the front and the back, like we talked about before. So the conservation of momentum is really, really important in this argument. Okay, we're getting there. So now you have a formula PV equals m v1x squared plus v2x squared plus v3x squared, and so on. Now you're like, how in the world am I going to do this sum, especially if I have 10 to the 23 particles like in a mole of gas? This seems really, really impractical. And for that, we need to start thinking a little bit more statistically. So let's start thinking about averages in order to make our life easier so we don't have to calculate 10 to the 23 velocities. So let's think about how to deal with this sum on the right-hand side. So I'm going to start thinking about averages. So let's introduce the average. I'm going to do it like this. Vx squared average. So the bar means average. So I'm average the velocity squared. What does this mean? Well, you know how to calculate an average, right? It's add up all of them and divide by the total. So it's v1x squared plus v2x squared plus v3x squared plus v4x squared, so on, divided by the total number of particles. Be careful. So notice what I'm doing is I'm averaging the squares. So caution. Average of the squares is not equal to the square of the averages. So I'm squaring first, adding them and dividing by the number. I'm not averaging first and then squaring it. So just be careful. If I write v squared bar, that means the average of the squares. It's not the same as v bar squared. That would be the square of the averages. Okay. So now let's use this above and plug it in. So PV is equal to m, and then the thing in parentheses here is the sum of all of those squares, which is Vx squared averaged times n. So bringing this n over to the other side. That's what I did. So right there we have a pretty interesting formula. Pressure times volume is mvx squared times n, which is the number of particles. So So what we did so far was only focused on the x direction. This was the pressure on the left wall, right? Well, what if I went ahead and did the whole thing again, but did the top and the bottom? So like I looked at the pressure on the top wall. That would look something like this, right? P times V. Everything would be the same except here this would be Vy squared, right? Times M. This would be on the top wall. And then what if I did the front and the back wall? That would be P times V is equal to M Vz squared bar times M. And this would be the pressure on the front wall. But the pressure in a gas is always the same no matter which wall I'm looking at, right? The pressure in the room that you're sitting in right now, the pressure on the front wall in front of you is equal to the pressure on the wall to the left of you. So that's why I use the same P for all of those. And then what I'm going to do is I'm going to add these three formulas together. So I'm going to add those up just to make a formula which is a little easier to digest. It doesn't have to have X, Y, or Z in it. So I will have, on the left, I have 3 PV. So I added them up, and I'm going to have here M times N, Vx squared bar plus Vy squared bar plus Vz squared bar. Well, what does that remind you of? X squared plus y squared, the x component squared plus the y component squared plus the z component squared. That's just the magnitude of the speed squared, right? So this quantity here is just the whole speed squared averaged. So I get 3pv is equal to mn v squared bar, average of the speed squared. And sometimes you might see this written a little differently. So you might see this written like PV is equal to 1/3 MN. And then sometimes people write this VRMS squared. So RMS means root mean squared. So VRMS is the square root of the averaged squared, right? So mean squared. So squaring them up, or squaring them and averaging them, and then taking the square root. So VRMS squared is equal to this notation that I'm using, V bar squared. Okay. So the formula that I just wrote is really interesting because it has, on the left side is macroscopic things, pressure and volume. So those are the things we've been talking about earlier in the course, things you can measure by eye or with macroscopic instruments. And on the right side, I have microscopic stuff, the mass of one particle, the number of the particles, the speed, the average speed squared at which the particles are moving. So I've related with this model the stuff on the left, which is macroscopic, to the stuff on the right, which is microscopic. I've made a connection between the macroscopic world and the microscopic world through this model of a gas as being composed of a bunch of hard spheres bouncing off of each other, conserving momentum and energy. Okay, let's go a little bit further to talk about temperature.